Hello and welcome back to this very short little update. So in my recent Stormlord Commodore 64 Games memories video, I noticed that there seemed to be some bootloader code which was in the memory as the game was starting, but I couldn't quite get it to run, and I wanted to try and get it to run, and I poked around a little bit more and found out how to get it running. So this is just a short update video regarding that. So if I take the Stormlord program and let it decompress in memory and start running the game as normal, and it spends quite a lot of time decompressing, you can see here that it's showing the Stormlord by Nick Jones intro screen and waiting for any key to start. We can see here that in the memory 8000 hex, using the lowercase ROM character set, we can see that there's some kind of screen here with what looks like what should have been a CBM80 hardware reset vector at the 8000 hex, and with some code here. So this is what I was looking at before in the previous video. So if I go back to my notes, what I do first is that I'm going to set a breakpoint at a particular address, because I don't want the code to quite go all the way into this game startup screen. So the breakpoint that I want to set is going to be at 1B, very low down in very low 0-page memory. So I'm going to let's rerun the game. Let's allow it to decompress all of the code into memory. Now, the reason why we're starting with a breakpoint very early on is that I did notice that if it started to execute even further, so if we open up the code here, there we go, and have a little look, I noticed it was starting to store stuff into memory and actually blank out some portions of this memory too, which I didn't like the look of. So what we're doing here is that we're stopping very early on in the execution, so that the game code does not have a chance to corrupt some of this memory around here. Now, when I was looking through the code for what this bootloader seemed to be doing, it seems to want to start after a machine reset at 83F1. This is a low and high byte, so we swap them around. This looks like code. This is definitely code, and I was going through this in the previous video as well. So when I was debugging this, I actually want to stop it from zeroing out 8004, which is the C portion of what should have been CBM80 in memory, which is what you can see here. This should have been a reverse CBM80. So I'm going to nop out using 3 no opcodes, EA each of them. So I'm going to nop out this first of all, and you'll be able to see what happens when I not them out as well. If we go to the disassembly and we scroll along here, 83, as long as the disassembly window, boink, there we go, 83F1 here. Right, I'll just put a little breakpoint here, but I'm going to be knopping out this instruction here. Hopefully the disassembly window stays in the same place. So 8800 83F7 EA boink. And of course the disassembly window has moved. Funny that. There we go. I've just knocked it out. Okay. I also want to nop out some of the 0-page initialization code. So not this is screen memory initialization code, but I did notice that it was also storing stuff over 02 and 03, and I noticed that the bootloader code was eventually jumping into code at 02 000300, so I want to also knock out this. 83FD, EA, and 8403, EA. And if we go back to the same place, we can see now that those stores into 0-page memory have been knocked out here and here. So if I remove those breakpoints, well, I'm going to put the breakpoint there back again, because what we can do now is that I can just tell the emulator to do a soft reset, not a hard reset, because I don't want to clear the memory. I want to reset the machine. This is effectively the same as pressing a reset button on the user port. It causes the CPU to start executing its reset vector initialization routine, which will then go through the kernel, and then it will intercept, it will notice that this is CBM 80, and it will start executing. But what I really need to do is that I also need to restore the reverse C. There we go. Now the kernel, when it boots, it will notice this is CBM80, and it will start the code at the vector, which is 83F1. In theory. So if I do a warm reset now, bing, we can see that the kernel has, or something has called into the code at 83F1 now, which is exactly what we want. What called into our code, or their code at 83F1, is a whole bunch of kernel setup stuff, which basically detects whether or not there is CBM80 at 8003 plus 1, which is 8004, for a few bytes, and if it is that, then it jumps into the indirect address, which is at 8000 in hex, which is 83F1. So this is precisely what we expect to see if the kernel is running our code correctly. So I'm just going to let the code continue on executing at this point. And there we have it. We have copyright 1985 to 1987 PD Systems Limited with a PD logo and Systems 6502 download software installed. We've got a nice green screen with some scrolled screen garbage down at the bottom here, but that's perfectly fine. That's actually kind of like the default screen that you would expect to see as the kernel was going through its reset routine. And if I remember rightly, the kernel changes screen colors and or scrolls the screen or something like that to indicate various stages through the boot process, and it has a few different states, maybe 2 or 3 if I'm remembering correctly. I'd have to check and actually look in the kernel disassembly if I wanted to really make sure, but we're not going to go into that in too much detail right now. So it's not doing anything right now. So what is it doing? Well, it's actually executing the code here. So it's running around in this very small, tight little loop, and we can see that if we look at the registers, we can see that the interrupts are on. In other words, the interrupts are disabled. The interrupt flag is set, so the interrupts are disabled. The CPU thinks it's already inside an interrupt. So nothing else is going to interrupt it apart from a non-maskable interrupt, of course. But you can see here that it's actually doing load with DD00. It's doing an EOR with 8, inverting a signal level coming in. Now I know that DD00 is actually the second CIA chip, and it is port A, not port B. And the second CIA chip, port B, is actually connected to the user port. We can see that on the schematic here. If we have a look at the schematic, this is DD00 CIA to port A bit 2, because port A bit 2 corresponds to the AND with 4, and then it does a branch on not equal back to here. So it's reading bit 2, counting from a 0, using 0 counting basis as well, obviously. So 0, 1, 2 is 1, 2, and 4 in hex, because we're translating binary to hex, and so we're ANDing it with 4. So it's detecting PA2. PA2 in the Commodore 64 schematic on CIA2 DD00 is port A bit 2, which is connected to M on the user port. If we have a look at port, so pin or edge connector M on the bottom side of the user port is labeled PA2 in the C64 Programmer's Reference Manual, Chapter 6, page 360, roughly, okay? And we can see here that it confirms that the port A is connected here with the labeling, port B is connected here. So CIA2 has full control over at least all of the 8 bits on port B and some of the bits on port A. Don't forget that also in the Commodore 64 Programmer's Reference Manual, it will tell you that the first 2 bits of DD00 are connected to the VIC bank control selection. And that's true. If we go back, so bit 2 here, we're confirming that it's actually connected to what's labeled also as the RS-232 TXD line. If we look at the schematic, we can see that PA0 and PA1 are actually connected to the VA address, which is video address, a VIC address or something like that, going into 14 and 15, which enables it to select the top 2 bits of the address being used by the VIC. So we can see here that CIA2 is actually controlling the graphics display using those first 2 bits. So that's why we look at PA2 here, which is connected to M from here. So we can surmise that at this point in time, the PD systems code is looking for some kind of signal inverting the TXD line, or rather edge connector pin M on the lower side of the user port bus. If we wanted to, we could see hopefully, if we do a backtrace, we can see that actually the code at 249 was calling this routine. Now this routine is not going to exit, and this routine looks like it's waiting for something on the user port, and then it looks like it's doing a whole bunch of stuff with other user port levels. So DD01 is obviously port B. So it's loading whatever is in port 1. So what we can surmise here is that it's loading port 1 and then it's transferring X to A here. It's doing some handshaky stuff, so it's inverting a few signals here and there. It's setting some flag somewhere in 388, which is here. So actually it's altering the flag, which it EORs with, okay, that's fine, and because it's doing some self-modifying code here. But the important thing here is that it's loading 8 bits from port B, and then it's loading them into X first, and then it's transferring X to the accumulator and returning from the subroutine. So if we have a look at what is calling that subroutine, it's at 249 because we've just done a backtrace. That looks at the address which is on the stack. So if we scroll up a little bit here, we can see that 249 is as we would expect, JSR 384, and then it compares it for a value. And if it's not equal to a value, then it goes to 264 and it compares it to another value. So it seems that the PD system's handshaking routine is looking for B5, B4, 284 here. Oh, it looks for a B6, so B5, B4, B6, blah blah blah. And there doesn't seem to be any sequence to them. It just seems to be numbers in this range for whatever reason. Yeah, they're all kind of like roughly in sequence, right? Ding ding ding, 31E. 31E goes back to here, so it seems to 249. That goes back to 249, and 249 is the start of that loop that we were looking at earlier on. Yep. So this is the first one. So it just goes, okay, so these are just flow control values or something like that, commands if you like, coming from the user pod with a parallel interface. So there we go, that's what we can surmise from here. And I guess if I looked at the code in a little bit more detail, we could probably see that some of this code does various different kind of things, like, I don't know, I'm just guessing, but probably setting up memory addresses to start storing stuff to, or whatever, or where to execute from, or so on and so forth. Anyway, that's about it really. PD systems, bootloader screen, kind of like mostly got it working, just not going to bother going into the parallel port protocol in too much detail right now. So thank you very much for watching these kind of like crazy, slightly technical deep dive videos into my Commodore 64 Games memories. If you like these kind of thing, then please do consider liking or subscribing to this channel, and I hope to catch you again next time. Take care and have a great day wherever you are.